Okay, Jefferson, can you all hear me?
Yeah. Yes.
Okay, awesome. So let's get started with the first video and then we'll go from there, okay? This is our last in-class meeting. So after this, we are going to be online after Thanksgiving. Next week is Thanksgiving. The week after is going to be online. And then I'll be sending out instructions for the final project tomorrow, okay?
Will we still have Zoom meetings or we have no meeting?
I stand corrected, Wednesday. So you'll be receiving instructions for the final project on Wednesday, and then you should start like looking into it, and the final week will be the topic for the final project, which is linear regression. Was that a question?
Will we have a Zoom meeting or no meeting?
No Zoom meeting, it'll be all online.
Thank you.
Thank you, that's a good question.
No.
So we get started, okay?
Say that we have 4 siblings, right?
Okay, let's get started, Jefferson.
How to pick who should do the dishes each night. And so the oldest sibling, right over here, he says, "Oh, look, I'll just put all of our names into a bowl, and then I'll just randomly pick one of our names out of the bowl each night, and then that person is going to be," so this is the bowl right over here, and I'm just going to put 4 sheets of paper in there. Each of them is going to have one of their names, and he's just going to randomly pick it out each night. And then that's the person who's going to do their dishes. So they all say, well, that seems like a reasonably fair thing to do. And so they start that process. So let's say that after the first 3 nights that he, the oldest brother here, let's call him Bill. Let's say after 3 nights, Bill has not had to do the dishes. So at that point, the rest of the siblings are starting to think maybe, just maybe, something fishy is happening. So what I want to think about is, what is the probability of that happening? What's the probability of 3 nights in a row, Bill does not get picked? If we assume that we were if Bill was truly randomly taking these things out of the bowl and not cheating in some way, what's the probability that that would happen? 3 nights in a row, Bill would not be picked. I encourage you to pause the video and think about that. Well, let's think about the probability that Bill's not picked on a given night. If it's truly random, so we're going to assume that Bill's not cheating. So assume truly random, and that each of the sheets of paper have a 1 in 4 chance of being picked. What's the probability that Bill does not get picked? Well, the probability that Bill not picked on a night. Well, there's 4 equally likely outcomes, and 3 of them result in Bill not getting picked. So there's a 3/4 probability that Bill is not picked on a given night. Well, what's the probability that Bill's not picked 3 nights in a row? Let me write that down. So the probability Bill not picked 3 nights in a row. Well, that's the probability he's not picked on the first night, times the probability that he's not picked on the second night, times the probability that he's not picked on the third night. So that's going to be 3 to the 3rd power, or 3 times 3 times 3. So that's 27 over 4 to the 3rd power. 4 times 4 times 4 is 64. And if we want to express that as a decimal, so that is 27. That is 27 divided by 64 is equal to, and I'll just round to the nearest hundredth right here, 0.42. So that is equal to 0.42. And so this doesn't seem that unlikely. It's a little less likely than kind of even odds, but it's not, you wouldn't question someone's credibility if, there's a 42%, roughly a 42% chance that 3 nights in a row, Bill would not be picked. So this seems like, if you're assuming truly random, that it's a reasonable, your hypothesis that it's truly random seems, there's a good chance that you're right. There's a 42% chance you would have the outcome you saw if your assumption is true. But let's say you keep doing this and you trust your older brother, why would you want to cheat out his younger siblings? But let's say that Bill's not picked 12 nights in a row. So then everyone's starting to get a little bit suspicious with Bill right over here. And so they say, well, we're going to give him the benefit of the doubt, assuming that he's being completely honest, that this is a completely random process. What is the probability that he would not be picked 12 nights in a row? Well, let's just write that down. So the probability, Bill, and it's really the same stuff that I just wrote up here. Bill not picked 12 nights in a row. Well, that's going to be 3. You're going to take 12 3/4 and multiply them together. It's going to be 3/4 to the 12th power. And what is this going to be equal to? Well, let's see. If you take 3/4 is, I'll just write 3 divided by 4, which is going to be 0.75 to the 12th power. Now, this is a much smaller. This is now, this is going to be 0.3. I guess we could go to one more decimal place, 0.32, or we could say this is 0.032, I should say, which is equal to, so this is approximately equal to, let's write that, which is equal to 3.2%. So now you have every right to start thinking that something is getting fishy. You could say, well, look, if there was, and this is what statisticians actually do, they often just define a threshold, and hey, if the probability of this happening purely by chance is more than 5%, then I'll say, well, maybe it was happening by chance. But if the probability of this happening purely by chance was, and this is the threshold that statisticians often use is 5%, but that's somewhat arbitrarily defined. But this is a fairly low probability that it would happen fairly by chance. So you might be tempted to reject the hypothesis, that it was truly random, that Bill is cheating in some way. And you can imagine, if it wasn't 12 in a row, if it was 20 in a row, then this probability becomes really, 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 really small. And so your hypothesis that it's truly random starts to really come into doubt.
Is 5% kind of accepted? Yeah. 10%?
10%, 5%, 1%, depending on the circumstances. And if it is like something like designed for some space shuttle or something more important, it'd be like much different.
Let's say that you have a cholesterol test, and you somehow magically know that the probability that it is accurate, that it gives the correct results, is 99%. You have a 99 out of 100 chance that on any time you apply this test, that it is going to be accurate. Now let's say that you just magically know that. We're just assuming that. Now let's just say that you get 100 folks into this room and you apply this test to all 100 of them. So apply test 100 times. So what are some of the possible outcomes here? Is it for sure that exactly 99 out of 100 are going to be accurate and then 1 out of 100 is going to be inaccurate? Well, that's definitely a likely possibility, but it's also possible you get a little lucky and all 100 are accurate, or you get a little unlucky and that 98 are accurate and that 2 are inaccurate. And actually, I calculated the probabilities ahead of time, and the goal of this video isn't to go into the probability and combinatorics of it, but if you're curious about it, there's a lot of good videos on probability and combinatorics on Khan Academy. But I calculated ahead of time, and the probability, if you have something that has a 99% chance of being accurate, and you apply it 100 times, the probability that it is accurate 100 out of the 100 times is approximately equal to 36.6%. I rounded to the nearest tenth of a percent. So it's a little better than a third chance that you'll actually get all of the people are going to get an accurate result, even though for any one of them, there's a 99% chance that it's accurate. Now we can keep going. The probability that it is accurate, I'm just going to put these quotes here so I don't have to rewrite accurate over and over again. The probability that it is accurate 99 out of 100 times, I calculated it ahead of time. it is approximately 37.0%. So this is what you would expect. Getting 100 out of 100 doesn't seem that unlikely. Each of the times you apply, there's a 99% chance of being accurate. But it makes sense that you would expect 99 out of 100 to be even more likely, slightly more likely. So we can, of course, keep going. The probability that it is accurate 98 out of 100 times is approximately 18.5%. And I'm just going to do a few more. The probability that it is accurate 97 out of 100 times, I calculated all of these ahead of time, is 6%. So it's definitely in the realm of possibility, but the probability is much lower than having 99 out of 100 or 100 out of 100 being accurate. And then the probability, double quotes here, the probability that is accurate 96 out of 100 times is approximately 1.5%. And then the probability, and I'll just do one more, I could keep going, probably, there's some probability that even though each test has a 99% chance, you just get super unlucky, and that very few of them are accurate. Well, and you see what's happening to the probabilities as we have fewer and fewer of them being accurate. It becomes less and less probable. So the probability that 95 out of the 100 are accurate is approximately 0.3%. So this was just kind of I guess you could say a thought experiment. If we had a test that we know for sure that every time you administer, the probability that it's accurate is 99%, then these are the probabilities that if you administer it 100 times, that you get 100 out of 100 accurate. The probability that you get 99 out of 100 accurate, and so on and so forth. So let's just keep that in mind, and then think a little bit about hypothesis testing and how we can use this framework. So let's put all that in the back of our mind. Now let's say that you have devised a new test. You have a new test, and you don't know how accurate it is. You have a new cholesterol test. You don't know how accurate it is. You know that in order for it to be approved by whatever governing body, it has to be accurate 99. The probability of it being accurate has to be 99%. So it needs to have probability of accurate equal to 99%. You don't know if this is true, you just know that that's what it needs to be. And so you have your test, and let's say you set up a hypothesis. And your hypothesis could be a lot of things. And once you get deeper into statistics, there's null hypothesis and alternate hypotheses. But let's just start with just a simple hypothesis. You're hopeful. Your hypothesis is that the probability that your new test is accurate is this is your hypothesis, because you want that to be your hypothesis, because if you feel good about it, then you're like, okay, yeah, maybe I'll get approved by the appropriate governing body. So you say, hey, my hypothesis is that my new test is accurate 99, the probability of it being accurate is 99%. So then you go off and you apply it 100 times. So you apply your new test. You don't know the actual probability of it being accurate. You apply the test. You apply the test 100 times. Now let's say out of those 100 times, you get that they are accurate. You get that it is accurate, and you're able to use some other test, some for sure test, some super accurate test to verify your own test results. And you see that it's an accurate 95 out of the 100 times. So the question you have is, well, does the hypothesis make sense to you? Will you accept this hypothesis? Well, what you say is, well, if my hypothesis was true, if my test were accurate, 99, if the probability of my test being accurate is 99%, what's the probability of me getting this outcome? Well, we figured that out. If it really was accurate 99% of the time, then the probability of getting this outcome is only 0.3%. So if you assume true, if you assume hypothesis, I'll just write hype. If you assume the hypothesis is true, the probability of the outcome you got, probability of observed outcome, is approximately 0.3%. And so say, look, maybe it's definitely possible that I just got very, 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 very unlikely. But based on this, I probably should reject my hypothesis because the probability of me getting this outcome, if the hypothesis is true, is very, 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 very low. And as we go deeper into statistics, you'll see that there are thresholds that people often set for, if the probability of something happening or not happening is above or below some threshold, then we might reject a certain hypothesis. But in this world, you could see that, look, if my test really was accurate 99% of the time, for me to get, when I apply it to 100 people, it's only accurate 95 out of 100. If my hypothesis is true, that would have there's only a 0.3% chance that I would have seen this observation. So based on that, it might be completely reasonable to say, you know what, I might reject my hypothesis and look for a new test. I don't feel good about this new cholesterol test that I constructed. We are told a restaurant owner installed a new automated drink machine. The machine is designed to dispense 530 milliliters of liquid on the medium size setting. The owner suspects that the machine may be dispensing too much in medium drinks. They decide to take a sample of 30 medium drinks to see if the average amount is significantly greater than 500 milliliters. What are appropriate hypotheses for their significance test? And they actually give us 4 choices here. I'll scroll down a little bit so that you can see all of the choices. So like always, pause this video and see if you can have a go at it. Okay, now let's do this together. So let's just remind ourselves what a null hypothesis is and what an alternative hypothesis is. One way to view a null hypothesis, this is the hypothesis where things are happening as expected. Sometimes people will describe this as the no difference hypothesis. It'll often have a statement of equality where the population parameter is equal to the value, where the value is what people were kind of assuming all along. The alternative hypothesis, this is a claim where if you have evidence to back up that claim, that would be new news. You are saying, hey, there's something interesting going on here. There is a difference. And so in this context, the no difference, we would say the null hypothesis would be, we would care about the population parameter, and here we care about the average amount of drink dispensed in the medium setting. So the population parameter there would be the mean, and that the mean would be equal to 530 milliliters, because that's what the drink machine is supposed to do. And then the alternative hypothesis, this is what the owner fears, is that the mean actually might be larger than that, larger than 530 milliliters. And so let's see, which of these choices is this? Well, these first 2 choices are talking about proportion, but it's really the average amount that we're talking about. We see it up here. They decided to take a sample of 30 medium drinks to see if the average amount, they're not talking about proportions here, they're talking about averages. And in this case, we're talking about estimating the population parameter, the population mean for how much drink is dispensed on that setting. And so this one is looking like this right over here. Only these 2 are even dealing with the mean. And the difference between this one and this one is this says the mean is greater than 530 milliliters, and that indeed is the owner's fear. And this over here, this alternative hypothesis is that it's dispensing on average less than 530 milliliters, but that's not what the owner is afraid of. And so that's not the kind of the news that we're trying to find some evidence for. So I would definitely pick choice C. Let's do another example. The National Sleep Foundation recommends that teenagers aged 14 to 17 years old get at least 8 hours of sleep per night for proper health and wellness. A statistics class at a large high school suspects that students at their school are getting less than 8 hours of sleep on average. To test their theory, they randomly sample 42 of these students and ask them how many hours of sleep they get per night. The mean from this sample, the mean from the sample is 7.5 hours. Here's their alternative hypothesis. The average amount of sleep students at their school get per night is, what is an appropriate ending to their alternative hypothesis? So pause this video and see if you can think about that. So let's just first think about a good null hypothesis. So the null hypothesis is, hey, there's actually no news here, that everything is what people were always assuming. And so the null hypothesis here is that no, the students are getting at least 8 hours of sleep per night. And so that would be that. Remember, we care about the population of students. And we care about the population of students at the school. And so we would say, well, the null hypothesis is that the parameter for the students at that school, the mean amount of sleep that they're getting, is indeed greater than or equal to 8 hours. And a good clue for the alternative hypothesis is when you see something like this, where they say a statistics class at a large high school suspects, so they suspect that things might be different than what people have always been assuming are actually what's good for students. And so they suspect that students at their school are getting less than 8 hours of sleep on average. And so they suspect that the population parameter, the population mean for their school is actually less than 8 hours. And so if you wanted to write this out in words, the average amount of sleep students at their school get per night is less than 8 hours. Now, one thing to watch out for is, one, you want to make sure you're getting the right parameter. Sometimes it's often a population mean, sometimes it's a population proportion. But the other thing that sometimes folks get stuck up on, but the other thing that sometimes confuses folks is, well, we are calculating a statistic from a sample. Here we're calculating the sample mean, but the sample statistics are not what should be involved in your hypothesis. Your hypotheses are claims about your population that you care about. Here, the population is the students at the high school. What we're going to do in this video is talk about type 1 errors and type 2 errors. And this is in the context of significance testing. So just as a little bit of review, in order to do a significance test, we first come up with a null and an alternative hypothesis. And we'll do this on some population in question. These will say some hypotheses about a true parameter for this population. And the null hypothesis tends to be kind of what was always assumed, or the status quo, while the alternative hypothesis, hey, there's news here. There's something alternative here. And to test it, and we're really testing the null hypothesis. We're going to decide whether we want to reject or fail to reject the null hypothesis. We take a sample. We take a sample from this population. Using that sample, we calculate a statistic. That's trying to estimate the parameter in question. And then using that statistic, we try to come up with the probability of getting that statistic, that we just calculated from that sample of a certain size, given if we were to assume that our null hypothesis is true. And if this probability, which is often known as a p-value, is below some threshold that we set ahead of time, which is known as the significance level, then we reject the null hypothesis. Let me write it down. So this right over here, this is our p-value. This should be all we review. We introduce it in other videos. We have seen in other videos, if our p-value is less than our significance level, then we reject our null hypothesis. And if our p-value is greater than or equal to our significance level, alpha, then we fail to reject our null hypothesis. And when we reject our null hypothesis, some people say that might suggest the alternative hypothesis. And the reason why this makes sense is if the probability of getting this statistic from a sample of a certain size, if we assume that the null hypothesis is true, is reasonably low, if it's below a threshold, maybe this threshold is 5%. If the probability of that happening was less than 5%, then hey, maybe it's reasonable to reject it. But we might be wrong in either of these scenarios, and that's where these errors come into play. Let's make a grid to make this clear. So there's the reality. Let me put reality up here. So the reality is there's two possible scenarios in reality. One is that the null hypothesis is true, and the other is that the null hypothesis is false. And then based on our significance test, there's two things that we might do. We might reject the null hypothesis, or we might fail to reject the null hypothesis. And so let's put a little grid here to think about the different combinations, the different scenarios here. So in a scenario where the null hypothesis is true, but we reject it, that feels like an error. We should reject something that is true, and that indeed is a type 1 error. Type 1 error. You shouldn't reject the null hypothesis if it was true. And you could even figure out what is the probability of getting a type 1 error? Well, that's going to be your significance level. Because if your null hypothesis is true, let's say that your significance level is 5%. Well, 5% of the time, even if your null hypothesis is true, you're going to get a statistic that's going to make you reject the null hypothesis. So one way to think about the probability of a type 1 error is your significance level. Now, if your null hypothesis is true and you fail to reject it, well, that's good. We could write this as, this is a correct conclusion. The good thing just happened to happen this time. Now, if your null hypothesis is false and you reject it, that's also good. That is the correct conclusion. But if your null hypothesis is false and you fail to reject it, well, then that is a type 2 error. That is a type 2 error. Now, with this context, in the next few videos, we will actually do some examples where we try to identify, one, whether an error is occurring and whether that error is a type 1 or a type 2. In the last video, our null hypothesis the drug had no effect, and our alternative hypothesis that the drug just has an effect. We didn't say whether the drug would lower the response time or raise the response time. We just said the drug has an effect, that it will not, the mean when you have the drug will not be the same thing as the population mean. And then the null hypothesis, no, your mean with the drug is going to be the same thing as the population mean, has no effect. In this situation, where we're really just testing to see if it had an effect, whether an extreme positive effect or an extreme negative effect would have both been considered an effect, we did something called a two-tailed test. This is called a two-tailed test. Two-tailed test. Because frankly, a super high response time, if you had a response time that was more than 3 standard deviations, that would have also made us likely to reject the null hypothesis. So we were dealing with kind of both tails. You could have done a similar type of hypothesis test with the same experiment where you only have a one-tailed test. And the way we could have done that is we still could have had the null hypothesis. We still could have had the null hypothesis be that the drug has no effect. Drug has no effect. Or that the mean with the drug, and maybe I could say the mean with the drug, is still going to be 1.2 seconds, our mean response time. Now, if we wanted to do a one-tailed test, for some reason, we already had maybe a view that this drug would lower response times, then our alternative hypothesis, and just so you get familiar with different types of notation, some books or teachers will write the alternative hypothesis H1, sometimes they write it as H alternative, either one is fine. If you want to do a one-tailed test, you could say that the drug lowers response time. The drug lowers response time, or that the mean with the drug is less than 1.2 seconds. Now, if you do a one-tailed test like this, what we're thinking about is, what we want to look at is, all right, we have our sampling distribution. Actually, I can just use the drawing that I had up here. You had your sampling distribution of the sample mean. We know what the mean of that was. It's 1.2 seconds, same as the population mean. We were able to estimate its standard deviation using our sample standard deviation. And that was reasonable because it had a sample size of greater than 30. So we could still kind of deal with a normal distribution for the sampling distribution. And using that, we saw that the result, the sample mean that we got, the one at 1.05 seconds, is 3 standard deviations below the mean. Is 3 standard deviations below the mean. So if we look at it, let me just redraw it with our new hypothesis test. So this is the sampling distribution. That's the sampling distribution. It has a mean right over here at 1.2 seconds. And the result we got was 3 standard deviations below the mean. 3 standard deviations below the mean. 1, 2, 3 standard deviations below the mean. That was what our 1.05 seconds were. So when you set it up like this, where you're not just saying that the drug has an effect, well, in that case, and that was the last video, you look at both tails. But here we're saying we only care, does the drug lower our response time? And just like we did before, you say, okay, let's say the drug doesn't lower our response time. If the drug doesn't lower our response time, what was the probability, or what is the probability of getting a lowering this extreme or more extreme? So here it will only be one of the tails that we consider when we set our alternative hypothesis like that we think it lowers. So the if our null hypothesis is true, the probability of getting a result more extreme than 1.05 seconds. Now we are only considering this tail right over here. Let me put it this way: more extreme than 1.05 seconds, or let me say lower, because in the last video we cared about more extreme, because even a really high result would have said, okay, the mean's definitely not 1.2 seconds. But in this case, we care about means that are lower. So now we care about the probability of a result lower than 1.05 seconds. That's the same thing as sampling from the sample, of getting a sample from the sampling distribution that's more than 3 standard deviations below the mean. And in this case, we're only going to consider the area of this one tail. So this right here would be a one-tail test, where we only care about one direction below the mean. And if you look at the one-tail test, this area over here, we saw last time that both of these areas combined are 0.3%. But if you're only considering one of these areas, if you're only considering this one over here, it's going to be half of that, because the normal distribution is symmetric. So it's going to be 0.13%. So this one right here is going to be 0.15%, or if you were express it as a decimal, this is going to be 0.0015. So once again, if you set up your hypotheses like this, you would have said, if your null hypothesis is correct, there would have only been a 0.15% chance of getting a result lower than the result we got. So that would be very unlikely. So we will reject the null hypothesis and go with the alternative. And in this situation, your p-value is going to be the 0.0015.
Okay, that's it for tonight. We covered just about everything on our learning objectives. I posted the homework for chapter 9. That's the only assignment for this week. So that's it. If you have any questions, please email me. I'll be happy to answer your questions. Jefferson, did you have any questions?
No. Thanks.
Okay. You all have a good night.
Zeit,